Um, he will give a talk about mixtures with varying concentrations. Okay, you can start.
Okay, thank you. So, hello everyone. I'm going to talk about nonparametric regression estimators for mixtures with varying concentrations. So, first of all, I'm going to do some introduction in models of mixture. I'm going to state a nonparametric regression problem, some previous results for non-mixture case and the case for the mixture with varying concentrations. And I'm going to give some theoretical results and proofs for them. So, statistical analysis of real data, an observable population is usually a mixture of subpopulations, also known as components of mixture, with different distributions for the observed variables. If the index of component which object belongs to is unknown, the distribution of object's features is derived from the mixture of distributions for different components, so conditional distributions. In finite mixture models, like see the reference for McLachlan and Peel and also Titterington, the mixing probabilities are the same for all observations. So they are constant, regardless of specific observation. So in the most flexible model of mixtures with varying concentrations, these mixing probabilities are different for different observations. You can see more about model of mixtures with varying concentrations in monography of my brother Sulakova, and also you can see in my brother and Sulakova work from 2012, and also Pidnipasna et al. 2023 for applications in medical, biological, and sociological studies. So we're going to talk about a mixture of regressions with varying concentrations. So in this framework, we observe two variables for each subject. One is regressor and another one is response, and they're linked via regression relationship. We have to estimate the non-regression functions that describe each relationship for each component of mixture. For estimation, we consider another Watson estimator proposed in Ditchko and my brother work, and a local linear regression estimator from Horbunov and my brother work. And for these estimators, we'll consider asymptotic behavior when sample size grows infinitely. So I'm going to talk some more about the mixture of concentrations model. What is it? So we can state it as follows. We can define it as follows. So we are observing n subjects denoted as OG, where each subject belongs to one of m subpopulations. Also, we can call it mixture components. The index of component for each subject is unknown, but we know the probability that a given subject belongs to m's component for any subject and for any component. These probabilities, PG and M, are called the mixing probabilities and also called concentrations of the components in mixture. So for each subject, we observe a set of variables, a random vector, d-dimensional vector, and let us denote as FMA a probability that a variable Xc takes values in set A, given that the index of the observable object equals M. This is a known distribution of this observed variable if our object belongs to the m's component. So this is our conditional distribution. Then we can rewrite our unconditional distribution for observed variable using the law of total probability. And also here we take A. This is a set from Borel sigma algebra on RD. We also assume that random vectors are mutually independent. This model is called a mixture with varying concentrations. The main question is how do we estimate the conditional distributions for Xi? We are going to introduce it via using the weighting coefficients. So first of all, we have to introduce some notations, some objects, recalling the results from my brother Shevchenko work. So we consider the triangle of a brackets operation. So we have an n-dimensional vector, and we compute the mean value based on these coordinates. Arithmetic operations inside the triangle brackets are performed element-wise. As you can see, for example, for the product of vectors. So let us define a gram matrix based on this triangle brackets operation. And a gram matrix is built for a set of concentration vectors Pm. So we assume that these concentration vectors are linearly independent. Thus, the gram matrix is invertible. And now we can introduce the minimax weighting coefficients defined via the minors of matrix gamma n. And also we can compute this weighting coefficients using the inverse matrix of for gamma n. And also further in our further talk, we will shortly introduce AM as a vector of minimax coefficients for the mth component. So here we actually can talk about where we can use our minimax weighted coefficients. So using these coefficients, we can build an empirical measure that can be used as an estimator for FMA given A. Also, we can observe that an averaging for AM and pk can be seen as some is equal to 1 when the indexes are equal and 0 otherwise. Considering this observation, we can show that such empirical measure is an unbiased estimator for the conditional distribution of Xi given that a subject belongs to the mth component of mixture. Also, we can note that this minimax weighted coefficients minimize the guaranteed risk that was built from the mean squared error. Also, we've talked about the general setting, about the mixture with various concentrations, and now we are ready to talk about the non-parametric regression problem. So, what actually changes? So, we are working in the framework of the mixture with various concentrations, and we assume that for each observable subject, we have a bivariate vector of numerical variables. Xj and Yj are regressor and response. The distribution of these variables is described by the following regression model as seen in equation 4. What can you see here? Here, Jk is a non-regression function for kth component of mixture. And also epsilon j is a random error term. What do we assume for this model? We assume that the vectors are mutually independent, as corresponds for the general statement for MVC. And also we assume that regressor and error are conditionally independent under the condition kappa j. That's our index for the j subject equals to m for any m given from 1 to m capital. Also, we assume that for any component of mixture, a conditional distribution for regressor has a probability density function fk. This PDF does not depend on number of subjects. And also, finally, we assume some conditions on distribution of errors. First of all, the conditional mean equals to 0, and also the conditional variance for the errors exist and they exist, they are finite. And also they does not depend on J. So what do we have to do here? Our main task is actually to estimate the non-regression function for given component of mixture. And how we can do this? In order to talk about the estimators for this model, we should go back and consider the homogeneous case. So in homogeneous case, we basically have, if we talk in terms of MVC, we have one component of mixture, and the regression function is basically the same for all subjects. So we take two estimators, another Watson estimator and a local linear regression estimator. Why? I'm going to explain later. So first of all, consider the classical Nadaraya-Watson estimator that is defined by the following formula. So what do we have here? We have here k stands as a kernel function and h stands as a bandwidth. We can interpret k as the weight of an observation in the estimator, and also bandwidth h can be interpreted as the width of the neighborhood around x0. X0, this is our point at which we estimate our unknown regression function, g of x. And also, what is the problem for this estimator? One of these problems actually is the following: that in homogeneous case, Nadaraya-Watson suffers from the boundary effect. It suffers from severe bias at such points of data which are the jump points, which are the discontinuity points of the regressor's probability density function. Here you can see two examples. For instance, from the left you can see a case where regressors have uniform distribution from 0 to 1. We have jump points at 0 and 1 respectively, and you can see that the Nadaraya-Watson estimator plot estimator has a severe bias when we are getting closer to either 0 or 1. Let us consider another case when regressor is represented as a mixture of two uniform distributions with disjoint supports. And here we have for this kind of distribution a jump point at x equals 1/2. As we can see from this plot, Nadaraya-Watson estimator has bias from the original comparing to the original function. So how do we cure this problem? How can one overcome it? So one can apply the local linear regression estimator. And how this estimator is constructed. So first of all, we introducing the localized least squares loss. So for each term we are multiplying by the value of kernel, and also we are trying to minimize this localized least squares loss by B0 and B1. The result of this minimization, we obtain, assume that we obtain the minimizer for this functional, and we take the value of the first coordinate, B0. And this B0 hat is considered as the local linear regression estimator at given point x0. Doing simple algebra, we can show the following representation for local linear regression estimator as follows. This is some function of some weighted function, weighted sums. Also, I can tell about that for the local linear regression estimator that is extensively studied in works of Yankin Fan. For instance, see Yankin Fan 1993. So, for example, we are going back for the problem of boundary effect. And here we're comparing the local linear regression estimator and the Nadaraya-Watson one. For this case, we can see that the bias for the local linear regression is visibly smaller comparing to the Nadaraya-Watson estimator. So what are we going to do now? We are going to adapt these estimators for the framework of Mischie with Array concentrations. And we are actually going to examine this estimator, how the situation how the situation could change. So firstly, we are introducing a modified Nadaraya-Watson estimator that is proposed in Dichko and my brother work. How it is adapted. So we are basically taking a classical Nadaraya-Watson estimator, but instead in each term in numerator and denominator, we are multiplying by a corresponding minimax weighting coefficient. Also in Dichko and my brother work, several results, more specifically consistency and asymptotic normality, is obtained for such estimator in case when x0 is a continuity point of regressor's probability density function. It is also can be noted that the rate of convergence for the Nadaraya-Watson estimator for the continuity, the case of continuity point, equals to 1 over n to the power of 2/5 power. Let us fix that in our minds, and we are going to talk about it later. So now we modify local linear estimator. Modified local linear estimator firstly for the mod Mischie's varying concentrations is proposed in Horbunov Mayer work 2023, and how it was modified. So we are taking the weighted least squares functional. And here, for each term, we basically multiplying each term by the corresponding minimax weighted coefficient. Now, what do we have here? First, we have to note that these weighted coefficients can be negative, so this functional can be bounded from below. But we can preserve the logic that we used for the classical local linear regression estimator and construct the modified estimator by solving the following system of equations. Actually, verified the stationary point. And the first coordinate of the solution is defined as a modified local linear estimator for the MVC. So here I'm noting that this local linear estimator is constructed for the M's unknown regression function. What do we talk next? We can also use some basic algebra and find the explicit form of this modified estimator. It is also a function of the weighted empirical sums, each term multiplied by minimax coefficient. And we can also see that we can also make some connection between the modified Nadaraya-Watson estimator and the estimator being from local linear regression technique. So here it is. Here are our estimators. Here are our two modified estimators, and this is our this is our subject of research. The main question is how do they behave first of all, and how the situation could change if we consider the case of jump when we are estimating at the jump point of probability of the regressor's PDF for the MVC framework. So we are going to talk about the asymptotic distributions and the rate of convergence. And first of all, before talking about that, I'm going to introduce one theorem that is under specific conditions guarantees the asymptotic normality of weighted sums. So
And
what?
sorry, and if you have no mixture of concentrations and just use those local estimators, and we have a jump point in PDF,
Mhm.
then what will be the limit of your estimator?
So in a homogeneous case, homogeneous case, local linear estimator, in local linear estimator, we basically have some sort of coefficient that cancels out in numerator and denominator. So for the local linear regression, we preserve the consistency. And also the same case can be seen for the Nadaraya-Watson estimator. But the thing is how the rate of convergence changes considering different points of different points, whether this is a point of continuity of the PDF or this is a discontinuity point. So
And if you have a jump over PDF, then the limit will be mean value of left limit and right limit of PDF.
So sort of. So when we are going to talk more about the proofs, we are going to see that instead of specific values of the PDF given x0, we are going to have one-sided limits from the left and the right. So I'm going to talk about this when we are going to the proofs. Thank you for the question.
And the limit will be in between the left limit and the right limit of
Mm.
PDF.
Yeah, so we are basically should consider approaches from the left side and from the right side, but the obtained values when we investigated the consistency of this estimator will cancel out because, for example, for the local linear estimator, we firstly investigated each of the term how each of the term behave. Each of the term is I'm actually talking about the weighted empirical sum. The weighted empirical sum converges to some value, some coefficient, and if we have some and if the empirical sum contains, for instance, yg, we have some coefficient multiplied by a known regression function at x0, assuming that x0 is the continuity point of the unknown regression function, but so it makes sense why we have to estimate at such point. So yeah, and these coefficients from the numerator and denominator will cancel out. This result on consistency is presented also in Horbunov-Maybard work 2024. So it is actually described here and also described how do we get how do we obtain the consistency in a more detailed way.
Okay,
Good.
thank, thank you.
Okay. Okay. So I'm going back to the asymptotic finding the asymptotic distribution of the estimators. In order to talk about the asymptotic distribution of the Nadaraya-Watson estimator and local linear regression estimator, I am introducing a vector of weighted sums. Specifically, this vector of sums is used in Nadaraya-Watson and local linear regression estimators. So both of estimators can be considered as some functions of Sn. And what are we going to examine? We are going to examine the asymptotic distribution of the normalized version of such weighted sums. So what are we going to talk? First of all, we are going to introduce some notation, helpful notation, in order to avoid some complexities in our expressions. So we are introducing one-sided integrals with values of regressors PDF. Also, we are introducing some combinations of such integrals And also we introduce sigma dlux dy. Actually, some linear combinations of I dx dy. Here we can see these triangle brackets of am squared times pk. This is actually a limit, as can be stated further, a limit for the averaging operation as n go to infinity for the product of these vectors, am squared and pk. And also further we can see some integrals that are using the kernel function and also some combinations based on this that are using these integrals. Okay, so what is the theorem? So the following theorem establishes an asymptotic normality for delta nm. We assume that m and x0 are fixed values, and we consider the following conditions hold. First of all, we assume that for all components of mixture, one-sided limits exist both for regressive PDF, conditional PDF and also a non-regressor function. Next, we assume that there exists the following limits for triangle brackets. As we can see here, the product of am squared and also pk, and also there's an averaging for the products of am, pk1, pk2. I recall that am is a vector of minimax coefficients. pk1, pk2 are respectively vectors for concentration vectors for k1 and k seconds component of mixture. The limits exist and finite. We also assume that there exists a limit for the Gram matrix. Next, there's a condition on bandwidth. We assume that bandwidth depends on the size of sample, and in such way that bandwidth tends to 0 when n tends to infinity, but the product of n and h tends to infinity. Next, we assume that our kernel has finite support. And also we assume, and also we introduce conditions on some integrals that are using the kernel function. Next, we are talking about yet again, we are talking about the regression function that we have to estimate. We assume that it is twice continuously differentiable in some neighborhood of x0. We denote this as b. And also for any component of mixture, we assume that regressor's PDF, conditional PDF, and the unknown regression function are locally bounded. And we assume there's also an assumption for the force conditional moment on the distribution of errors. Considering this, we have the asymptotic normality for the vector of weighted sums. With the asymptotic distribution has a multivariate normal Gaussian distribution with zero mean and the covariance matrix defined by the following, where the entries of this matrix are defined previously as follows: as the sum of products of the limits of triangle brackets and multiplied by idx dy, where idx dy also the combinations that are using the integrals of kz squared.
And this asymptotic matrix, can it be degenerate?
Yes, this matrix cannot be degenerate, and also when we are proving the asymptotic normality for the vector of weighted sums, we are using the Lindenberg's central limit theory. So with this in mind, we are assuming that this matrix is non-degenerate.
But in this theorem, it can be allowed to be degenerate.
That's actually a good point.
Maybe you need a condition that it is non-singular.
Yes, we can. Yeah, that's a good point because firstly we are going to check the conditions of the central limit theorem, and it requires a condition when the matrix, when the limit matrix is non-degenerate. So yeah, this condition should be mentioned. Okay, okay. Thank you for this. Okay. So how do we use this theorem for, how do we use the asymptotic distribution for our modified estimators? So firstly, we can use this. We can use this for when for investigating the asymptotic distribution of local linear regression estimator. We introduce additional assumptions on how do we choose the bandwidth parameter n to the power of minus one fifth times some positive constant h. Also, there is condition for the integrals. As these EPXPY are defined here. Some of the integrals. And also we assume that the following integral using the kernel function is finite.
It
Consider,
is better to write here modulus of z to the third
yeah,
power.
it's better to write this down. Yeah, I agree with this. Thank you. So considering these conditions in mind, the local linear regression is asymptotically normal, where the mean, the expected value and variance of the limiting distribution are defined by the following formulas. These formulas are quite quite complicated, so it is helpful. It is quite helpful to have some notations as introduced previously. What can we also note here that here in this case, regardless whether the x0 is a jump point or not, the rate of convergence for the local linear regression estimator is preserved, and it is of the order 1 over n to the power of 2/5. But what can we talk about the modified Nadraya-Watson estimator? In the continuous case, referring to the Dishko-Meyer brothers' work, the rate of convergence actually is 1 over 1 over n to the power of 2/5. But when we are considering jump point, this in this case, our rate of convergence deteriorates, and we have to adapt to this scenario. So first of all, we are considering yet again the assumptions from the first theorem on the asymptotic normality of the vector of sums. And also we assume that E00, that's yet again a combination of integrals, is not equal to 0. So in this case, considering these additional assumptions, the Nadraya-Watson estimator is asymptotically normal. But here the asymptotic expected value and the variance for the limiting distribution are given. The limiting distribution is Gaussian, and also note that the rate convergence is different compared to the, for example, for the local linear regression estimator. It is slower. So this is actually so case of discontinuity actually can deteriorate our modified Nadraya-Watson estimator.
And sorry, and it is not clear if we have a jump at x0 of this g function, and g is a density, yes?
No. G is a unknown regression function.
Unknown regression. Uh-huh. But
Yeah.
anyway, if you have a jump, what is the value at x0?
Value at
Com-
x0. So we are considering the value, consider the conditions of theorem 1. G at x0 given a fixed m
yeah.
is well defined. But for the k does not equal to m, jk at x0 is not defined since we is not necessarily defined since we only assuming that the one-sided limits exist. So we know we can compute, for example, the one-sided limits for jk, and this actually used for the how to express variance of the limiting distribution. And also considering that the x0 is a jump point, respectively in a0 k, we have one-sided limits for the conditional PDF of regressor's PDF.
But this again, this gm of x0, is it mean value of left and right limits of gm at point x0?
I hope that I am understanding your question clearly. So here GM of x0 it can be actually considered as mean value of one-sided limits since they're both equal. Yeah. Maybe I misinterpreted your question, so I can talk about it more in the end of my talk, if you don't mind.
Yes.
Good.
Okay.
Do it. So here we introduce the applications of the theorem on asymptotic normality of vector of weighted sums. And what's more, we've talked about that the modified estimators use kernel function at the bandwidth function. So, for example, for bandwidth parameter, for bandwidth parameter, we can derive a theoretically optimal approach. For example, for point-wise estimation. So, for example, consider modified local linear regression estimator. We, by theorem 2, that guarantees the asymptotic normality for such estimator, we have the following limiting distribution. And from this limiting distribution, we introduce an asymptotic mean squared error for this estimator. And what's more, we try to minimize the asymptotic mean squared error by H capital. Minimizing H capital, minimizing the asymptotic mean squared error by H capital, we obtain the theoretical optimal bandwidth choice for case of local linear regression estimator when the estimation is done at a given point, at a fixed point. So now we've done with some talk, and we are probably ready for the proofs. So I'm going to state an idea of proof for the asymptotic distribution of vector of weighted sums. This proof is basically some sort of standard because we are using the Lindenberg's central limit theorem and straightforwardly verifying whether these conditions hold. First of all, let me state the Lindenberg's central limit theorem. We have a set of random vectors and d-dimensional random vectors, and they satisfy the following assumptions. First of all, for any fixed n, set of these vectors are mutually independent. Second, that they're centered. Third one, that there exists a limit for the sum of covariance matrices of each of the terms. This sigma squared can be used as the limiting covariance matrix of the limiting distribution. And also, you have an additional another condition for this sigma squared, that this matrix should be must be positive semi-definite matrix.
It is always positive semi-definite,
Yes.
because the sigma n squared are positive semi-definite. You can claim that it is positive definite, maybe.
Yeah, positive. Uh, Probably we should state it about positive definite matrix.
Yes,
Thank
then it will be a condition. Yes.
Mm-hmm. Uh, yeah, I agree with this. Thank you. And also, a final condition is called Lindenberg's condition, and we verifying whether the sum of these expected values tends to zero. And with these assumptions in mind, a sum of these random vectors has a limiting distribution, Gaussian limiting distribution with expected value 0 and covariance matrix defined by sigma squared. Proof is given in, for example, in Borovkov. So how do we prove it? First of all, we have to rewrite our vector of sums as a sum of random vectors. So here we rewrite the SN using with eta jn m. And here we introduce some additional notations that that will be used furtherly. So we are verifying the conditions of COT for eta j to n m. And also we will denote the condition the random variables tilde eta m as a distribution of eta j m conditioned on kappa j equals m. The first condition of the first and second conditions in COT holds. First one holds because of our assumptions that xj and yj are independent for different j, and also the second condition basically follows from the construction of eta jn. Because in this vector is actually our minimax coefficient multiplied by the centered vector eta tilde. Now we have to do more interesting part. We have to verify the third condition. We have to find the limit of sums of covariance matrices. And in order to do this, we consider some integers, non-negative integers as given here. And we investigate separately each entry in our matrix. So we investigate here we investigated covariance of the empirical sums. We can rewrite this covariance as the difference of two terms. The first term contains sum of expected value of products, and the second term is sum of products of expected values. We will show furtherly that the first term converges. That the first term converges to an intermediate value, and the second term will vanish. So here, talking about the first term, Q1M, we find that it converges to the sum of the products. Here in the product we have I dx dy k. This is our combination of the of integrals, and here this is a limit of the averaging operation on squared am times pk. And how do we obtain that? First of all, we are investigating separately the conditional expected value. We are writing this via the using the known regressive probability density function, and also using the distribution for the errors. And the next step is actually applying the Lebesgue-dominated convergence theorem in order to obtain the following result. Next. So this shows the convergence for Q1, and the second one shows the convergence for Q second Q2 to 0. How we are proving this? Firstly, we rewriting the sum. First of all, we rewriting this expected values via the sum of conditional expected values with conditioning of kappa j equals k from from one to m capital. And here we have the following double sum, and the sum for j equals from 1 to m is rewritten in the averaging operation. Since this averaging has a limit, it is bounded, and now we have to talk about these functions that are used in the product. We are proving that these functions are bounded, considering that these functions jk and fk are locally bounded. Considering this, we are obtaining the sum is bounded, and from the left we can see that there is a bandwidth parameter actually h that tends to 0 as n tends to infinity. So here we have so this value is bounded, this tends to 0, and Q2 tends to 0, as n tends to infinity. So then we are proving the result that this covariance tends to the following sum, to the limit of the Q1 when n tends to infinity. This finalizes the third step, or in the verification of this third step. And the final step is to verify the Lindenberg's condition. The Lindenberg's condition can be verified. The Lindenberg's condition is sufficient to verify if we verify the following convergence for this expected value of minimum of norms to the power of 2 and power of s, and for some s greater than 2. And also we verify whether convergence of this norm power to the power of p tends to 0 for p greater or equal than 2. It is quite easier to show the convergence 8. How we can do this? We can apply, for example, the following. First of all, we are rewriting this norm as by definition, this is the square root of sum of squares of the coordinates. Here, each of these e capitals represents the squares of the coordinates. Next, each of these terms we can bound by h divided by n and multiplied by square of the integral. And this is equals to this ratio times c times some constant, where this constant depends on the regressor's probability density function and some integrals that are using kernel function, and also there can be some there can also appear unknown regression value of unknown regression functions. If we consider, for example, here a term that uses yk with non-zero power. Considering this, so we obtain a general bound for this norm times n to the and this norm to the power of p, and we also know that this constant is bounded. And the final step, we are showing that this term, this multiplier tends to 0, considering the assumption 4 on how do we choose the bandwidth parameter. This proves actually the convergence 8. in order to prove the convergence 7, we are applying first of all the following bound for the expected value of minimum, taking arbitrary tau greater than 0. And the next step, we have to show that here the 10 is n times expected value of quadratic norm of the vector with an indicator. That we have to show, first of all, that the 10 0 is bounded at the 10 tau tends to 0 as n tends to infinity for any positive tau. So how we can do this? First, we are going to apply Lebesgue dominated convergence theorem for what? So we are basically rewriting the 10 tau explicitly using our conditional PDF for regressive function, and also we are rewriting this considering that the with conditioning on kappa g equals to m, our regressor and our error are independent. The next step is lies in also trying to bound our function v times times our conditional PDF. We can bound it by the following, and we can also show that this measurement is integrable. And from this we can show that the 10 at 0 is bounded. And next, using this result, we can apply Lebesgue dominated convergence theorem to prove that n of tau tends to 0 as n tends to infinity. Why it tends to 0? So the integrand here is basically v times fk times this indicator. This indicator tends to 0 since tau square and h tends to infinity, since n h tends to infinity. The measurement can be found in a similar way as we were proving the why the 10 at 0 is bounded. So with this in mind, Lebesgue dominated convergence theorem holds, and that's how we prove this part convergence 7. And taking convergence 7 and 8, we are proving the Lindenberg's condition. Good. That's for the first theorem on the asymptotic distribution of weighted sums.
Sorry, can you show the previous slide?
Yes.
And before previous.
Yet another, yeah.
Where you have two lines that n times some minimum tends to 0, and below n times expectation tends to 0. Can you show that slide?
Yeah.
Yes, this
Yes.
one. And imagine that you proved 8. I think that you can immediately obtain 7, because minimum of two values is less or equal to the sum of those values. And each summand tends to 0 due to condition 8. Then you need not do your transformations and so on.
Okay, so I can using the condition 8, I can possibly show that the 7 also holds. Am I right?
Immediately in one line.
Okay.
Yes.
I haven't tried that, to be honest, but I'm going to try that later after the talk.
Just
So
inequality, that minimum of two
uh-huh.
values is less or equal to the sum of those values.
Okay, thank you. I see.
But maybe I'm wrong, because
I'm going to check this. I'm going to check this. This is
because
actually
you have in 8 you do not have absolute value. It is not absolute moment.
Mhm.
Maybe I am wrong, but who knows? Okay.
Okay, I'm going I will verify this later, but this is actually quite interesting
Mhm.
proposal. Okay,
Maybe not. Okay.
yeah. So this actually finalizes my talk on the verifying the first conditions. So here I'm finishing talking about the proof for the theorem one, and now I'm going to talk a bit on the asymptotic normality, on how do we prove the asymptotic normality for a local linear regression estimator. In order to prove the asymptotic normality of such estimator, when we are doing this, first of all, we are decomposing our estimator to the sum of sum of sum of random vectors, sum of centered random vectors, and there is a part that can be called as a bias. And this lemma states how this bias, what is the asymptotic behavior of this bias. So here we have En M. This is our expected value of the weighted sums. As you can see here, En is actually expected value of this weighted sums. U is actually a function that is used for the local linear regression estimator. Local linear regression estimator is a function of Sm considering this function. Going back to the lemma, it can be shown that the asymptotic behavior of the bias as follows. So how we can prove this? So first of all, we write this bias, using the following representations of Cm. We introduce the following notations for Cn and Dn. And next, we are rewriting Cn and Dn in an integral form. Since we can do this, yeah, and later using these integral representations for Cn and Dm, we are trying to investigate an asymptotic behavior. How do we do this? So here I'm going to do an Taylor's expansion for the regression function I'm trying to estimate in the neighborhood of x0. Considering this in mind, this difference, and also considering these integral representations for Cn and Dn, can be rewritten as follows. And this integral can be decomposed as the sum of three following parts. So J1n, J2n, J3n are actually three terms corresponding for each of the terms on the previous in the previous part. Here, R of t is a remainder that is obtained from the Taylor's expansion. So what are we going to do? We are going to handle now these terms J1, J2, and J3. So first of all, it can be shown that the first term equals to 0 because we can basically rewrite the integrals and in a way that we can obtain these expected values. And we are basically from the one side and from another side basically obtaining the same value, which cancels out and we get 0. Next, we have rewritten the remainder. And what can we talk about the remainder? These expected values So these expected values have a limit under the conditions that are stated in our theorems. So we can so by continuity this also has a limit. So we know that this term is has a similar behavior as this term as given in a formulation of lemma 2. We get this from the J2. And now the main question, how we are handling the third term. So yet again, we are rewriting this term via the difference of integrals. And each integral is treated separately. And also we have to consider that our PDF or regressors PDF have a jump point at x0. So basically here we decompose this integral for the negative set from -a to 0 and the positive set from 0 to a. For instance, we are considering an integral on the positive on a positive interval. So it behaves as follows. If we consider it a negative part, so we've had the mostly similar expression, but here we have, but here we could have a right-sided limit and also different bounds for the integral. Next, we can bound both of the sides. Both of the sides, I meaning I decompose the integrals for the negative part and the positive part, and I am taking for example, this positive part. I can bound it by the following. For some n great enough, this integral exists. This integral exists, is finite, and epsilon is fixed. So here we have an order of smaller of h squared, a sentence to infinity. The same estimation can be done for the negative part in the same way. So combining two results, we obtain that this JR, so this integral, has the order of h squared. And from this, considering that for this expected values a to 0 and a1 0, for this terms the limit exists and finite, we can provide that the third term has an order of h squared when n tends to infinity, which proves the statement of lemma 2. So yeah, so this is basically we were talking about how we will handle the bias term, and finally we are talking about the synthetic normality of the local linear regression estimator. So here, as I said earlier, we are going to do the following. First of all, we add and subtract the value of function u. I recall that function u is used to represent the local linear regression estimator at a point when taking Sn as an input. And we have two separate terms. The first term is handled using the continuous mapping theorem and using the proving central limit theorem for the weighted sums, vector of weighted sums. And for the second part, for bias, we are using lemma 2 on how on the symptotic behavior of bias. So with this in mind, consider the first result actually gives us a limiting behavior of this term. This is actually a multivariate normal distribution with mean 0 and variance, as you can see here, s squared. And by lemma 2, from the second term, we obtain the mean value for the asymptotic distribution, as stated in the theorem 2. This actually finalizes all the proofs of the talk I wanted to do. So probably some of the steps were not clear, so you can ask, and thank you for listening, I guess. So the main result, we obtain the asymptotic distributions for both of modified estimators when we considering the case of jump points of the regressor's PDF. And we found out that for the local linear regression estimator, the rate of convergence remains the same. But on the other hand, for the Nadaraya-Watson estimator, when we have a jump point at which we have to estimate the non-regression function, the convergence of the Nadaraya-Watson estimator deteriorates. And that's our result.
Okay. Thank you for your interesting talk. And any questions, remarks?
I think there were questions during the talk. Sergey Shklar, what is f function here? Sergey, I think that it became clear what f stands for. Here, f stands for the conditional PDF of the regressor function. Of the regressor, I'm sorry. As we can see on slide 9, we are assuming that for each component of regression, we are assuming that conditional distribution of regressor, given that the index equals to k, has a probability distribution function fk. So in all further notation, further prose, fk is our conditional PDF of regressor for the case component. Okay.
Any other questions? And I have a question. So, theorem 2 is very interesting and quite unusual that the limiting distribution is not centered.
Yes, that is. I could tell this. This is quite like you can say common for the non-parametric regression analysis, because if you consider it as a case of homogeneous case, we could also obtain the asymptotic distribution with non-centered asymptotic distribution. So we regardless of the case, we should handle the bias term.
And can you construct confidence interval for GM of x0 using this theorem 3?
Yes, yes. Using we can using the result on asymptotic normality. I'm sorry. Regardless of that, we can build an asymptotic confidence intervals for JM at x0. Yeah.
But then you should know that the asymptotic variance does not equal to 0.
Yep. Yep. Yes.
You need some conditions to ensure
Yes.
that.
Yes, so going back to the theorem 1, we have to state clear on the conditions when the limiting. So first of all, for talking about the vector of the weighted sums, we have to make clear state when this limiting matrix is non-degenerate, and from this also the assumption on when the variance of the limiting distribution is non-degenerate. So yeah.
And do you have simulations?
Yes, I have simulations, but I will present it from my article. Let me just introduce one minute.
Just
Yeah. Here. I'm talking about the asymptotic normality of local linear regression estimator, and I have done the simulations for the following. Let me just go quickly to the simulation experience.
Just
Uh,
pictures.
yes. Uh, we have a regression. We have a mixture of regressions with two components. Concentrations are defined by by these formulas. Regressor's PDF is the same for both components of mixture and has a jump point that at t equals 1/2. Distribution of error terms are different for different experiments will be given below. And we consider as regression functions a sinusoid and cosinusoid. We've done the estimation procedure for x0 equals 1/2. And we were examining the simulated normalized bias and also normalized variance. In the same way as we've done for as we normalized for the local linear regression estimator. And we were checking how the bias and standard deviation, this normalized standard deviation, the behavior of this measures. I'm sorry. For the local linear regression estimator, we were using a theoretically optimal approach for the bandwidth based on the minimizing cost of asymptotic mean squared error of the limiting distribution. And we were using the Yabonechnikov kernel as defined. It defined as follows. And we were we were noting that for the first component of mixture, theoretically optimal bandwidth does not exist since bias equals 0. So we could not construct from the asymptotic mean squared error an optimal, theoretically optimal bandwidth. So for this case, we used the same H capital as used for the second component. And here below we have the simulation results for the normalized bias and variance. In the row with labeled infinity, we stated the theoretical asymptotic mean and asymptotic mean and asymptotic variance. So I'm talking about the mean value and square root of variance for the limiting distribution. And we can see if we consider larger sizes of sample sizes, the behavior is here for this example. We can see that we have the expected results. Here for this result M1, we have to refer what we are talking about in table 2. In table 2, we consider the heavy-tailed distribution of errors, and thus we have thus we had some quite interesting results for the first component. And for the second one, we obtained the results quite similar to the expected ones. And the third one is actually a combination of the first result. In the first result, we considered the normal distribution of errors. In the second result, we considered the t-distributed errors. And here we consider a mixture of errors of normal distribution and students distribution. And we have the following results that for giving the larger sample sizes, we have a normalized bias and variance quite similar to the theoretical ones. So that's it. That's it for the simulations. Yeah. And
Okay.
probably if any other questions, please ask.
Yes. Okay, maybe Rostislav Evgenievich will tell something.
No, I have no questions and no remarks. You see, uh, it was a nice report, and all what I can say, Daniel says for me. Okay.
Yes, I like these results, and sometimes your proofs are quite technical. You made a tremendous job to prove those theorems. Thanks again for your talk.
Thank
And
you.
next time we will have an interesting talk about behavior of minimum points of functionals. It will be just a kind of functional analysis or mathematical analysis, but it is useful in statistics because typically our estimators are defined using minimization technique. So I think it will be interesting next week. Okay. Uh-huh. Okay, then we can finish our session.
Thank you.
Okay,
Goodbye.
so goodbye
Goodbye.
to all.
Yes.